In this collection of videos, we are going to introduce the concept of definite integrals and discuss their relationship with area. So I wanted to start out by giving a motivating example. Imagine that we have some sort of curve f of x, which I've shown here, and we want to find the area between the curve f of x and the x-axis. For a shape such as this one, we could go ahead and break up these trapezoidal shapes into smaller shapes that have more easily memorizable area formulas like triangles and rectangles. We can then compute the area using 1/2 the base times the height for our triangles, or the base times the height for our rectangles. We can compute the areas of each of these individual pieces and perform a sum to determine this area. This method is pretty straightforward, and so this problem is relatively simple, which makes us happy. However, if we change our curve f of x from something that can be decomposed into very nice geometric formulas to something a little more complicated, we attempt to apply the same concepts and things get a whole lot messier. We can put a rectangle underneath this large portion of curve over here and over here, but those rectangles aren't a very good approximation for the curve. The heights are somewhat difficult to figure out, and we can try and approximate these remaining regions with triangles, but the shape isn't exactly precise, and the measurements are a little bit difficult as well. And these 4 red numbers that we're displaying here are also ignoring this area up here, which has a much harder to determine shape. And again, if we wanted to, we could probably use a triangle to approximate this area that we have over here. But as you can see, our computations have gotten a lot messier, and we're no longer finding the exact area that's lying underneath this curve, but rather we're getting a kind of messy, sloppy approximation, which makes us pretty sad. So the method that's going to drive what we're going to be doing is a simplification and a cleaning of this process. Instead of looking at all different types of geometric shapes that we could throw underneath a curve, what we're going to do is restrict our attention to rectangles. After all, rectangles have a very easy to understand area formula. It's one of the ones from geometry we can remember off the top of our heads. And in order to compensate for the fact that a rectangle may not be the most natural fit for what we want to put underneath a curve, we're going to put lots of rectangles underneath that curve to try to best fit the shape of the graph f of x. This method is a little bit of a compromise as is, because we've simplified the geometry that we may need to know. We don't need to worry about finding area formulas for triangles and trapezoids and maybe circles. We just have to remember the area formula of one type of very basic shape. That makes us a little bit happier, but seeing lots and lots of these intermediate computations that we're going to have to do makes us a little bit sadder. So it's kind of an in-between method for now. As we continue on in the course, we'll find a method that makes us very, very happy. So let's be a little bit more precise in what we're doing here. Let's imagine that we have a curve written down by f of x, and let's assume that we're working along the x-axis on the interval from a to b. So this thing that I have denoting x naught over here, we should think about as being the point A on the x-axis, and this point over here, x sub n, we want to think about as being the b value on the x-axis. And what we want to do is use n rectangles of equal width to approximate the area underneath the curve f of x and between the x-axis from this point A to this point B. The overall process that we're going to use here is very simple. We're going to determine the width of each rectangle, the height of each rectangle. We're going to use the area formula to then determine the area of one of these rectangles. And last but not least, we'll add all the individual areas up to get our approximation for the area that we want to find. First, let's determine the base of a rectangle. And because we're using rectangles of equal width, all of the base measurements will be the same no matter what rectangle we pick. Now here, our entire length of the interval is our ending point minus our starting point, b minus a. And we're breaking up that distance of b minus a into n pieces, 1 unit for each of the rectangles that we want to consider. So the width of any one of those rectangles can be given by the expression b minus a over n. Again, notice that this doesn't matter what rectangle we're considering. That measurement of the length of the base is always the same. Because of that, and because this b minus a over n is a fraction, and fractions are a little clunky to write down on a sheet of paper, we're going to abbreviate this small distance as dx. Also integral to determining the area of a rectangle is its height. And we can see that these rectangles, while they have widths that are all equal, their heights are all different. And what's determining the height of any individual rectangle is the value of a function at one of the endpoints of the rectangles. From the picture we have here, you can use this rectangle existing in between the space between x0 and x1 as an example if you'd like. What's determining the height of this rectangle is the height of the function at the rightmost endpoint of this little interval. So for this first rectangle, it's the value of the function evaluated at the x1 point. So in general, if we were picking out the ith rectangle, the value of the function on the input of x sub I is going to give us a formula for the height of the ith rectangle. Finding area from this point is very straightforward. To find the area of the ith rectangle, we just multiply its base times its height. And the last component is to sum up all of the individual areas of the n different rectangles we have. So starting at the first rectangle and stopping at the nth rectangle, we want to add up the expression f of x sub I multiplied by dx for the height times the base. Now where this particular story ends for now is that it's clear to us, going back and forth from one picture to another, that the approximation of the area between the function f of x and the x-axis is going to get better the more rectangles we put underneath the curve. So the difference I've shown from this slide, from the previous slide, is that I've doubled the number of rectangles under the curve. And you can see that the gaps between the rectangles and the curve get smaller when I do that. So if we take a calculus approach to this problem and shove more and more and more rectangles underneath the curve, what we'll get is this expression on the right-hand side of this equation over here. This expression with the sigma and the height and the base of the rectangles is always describing the total area for us, and the limit sign in front is indicating that we want to put more and more and more rectangles underneath that curve. And as we do, this value, including the limit over here on the right, is going to eventually converge to the exact value of the area between the curve f of x and the positive x-axis as x goes from A to B. And it's this limit value that we're particularly interested in. And because this right-hand side of this equation, which makes sense to us as it is derived, but is very clunky to write repeatedly, we're going to introduce a new notation for that, which I've written over here on the left-hand side of the equation. The way that we say the left-hand side of this equation out loud is that it is the definite integral of the function f of x on the interval from A to B. So it's having these little number values, A and B right here, that make this expression over here on the left what we call a definite integral as opposed to just an integral. And all this notation means is that it's a shorthand for the thing over here on the right-hand side of that equation.